Good day, everybody. I'm Amy Lambert, and I'm EA's Director of Communications. Welcome to this, our first in a series of webinars that we are hosting as part of our 50th anniversary. EA was founded in 1973 by Dr. Lauren Jensen as ecological analysts. The company has grown from a small single office in Baltimore to a geographic footprint spanning the US and its territories. Along the way, we became 100% employee-owned, public benefit corporation. In line with our core purpose of improving the quality of the environment, we're excited to share our expertise in managing dredging debris. Now, I'd like to turn this over to our speakers, Jamie Beaver and Matt Bowman.
Thank you, Amy. Good afternoon, everyone. Thanks for joining us. I'm Jamie Beaver. I'm a senior engineer at EA. I've been involved in contaminated sediment remediation for about 27 years now. We are also joined by Matthew Bowman, who will introduce himself when he takes over for the second part of the presentation. So I'll be speaking about some of the considerations for planning dredging projects relative to debris, so the investigations through design. Matt Bowman will be speaking more to the construction considerations. So next slide, please. We would like to start with acknowledgements. So this process has actually been about a year in the making at this point. So myself, Matt Bowman, Mike Carlo with EA, Don Hayes, and Mike Palermo, we wanted to delve more deeply into the idea of debris and what that means for environmental dredging. As part of that, and kind of combining our collective experience with debris issues for environmental dredging, we wanted to gain the insights of contractors and integrate their perspectives into this work. And ultimately, this culminated in a conference paper that was presented for the Western Dredging Association National Conference last year. We'd like to thank the contractors listed in this slide for providing input to our debris questionnaire. We'd also like to thank EPA Region 5, Great Lakes National Program Office, for allowing us to use project materials, project slides and photos, and the core Detroit District for the ROV photo and video that we'll show in subsequent slide. Next slide, please. So why is debris an important topic for environmental dredging or sediment remediation in general? We'll see in the next slide how important sediment disturbances are in the process of remediation, environmental dredging in particular, and debris can be an impact to that. Debris can also affect the operation side of dredging, resulting in additional project costs and extended construction schedule. And it can be an important factor in the achievement of remedial action objectives in some cases, particularly if there are significant quantities of debris. And we'll speak to that in the upcoming slide. This is not just a consideration for dredging, it also impacts other remedial alternatives such as subaqueous capping. Next slide, please. So within the WEDA paper, we started by really trying to compile and assemble all the information in the context of what do we know about debris for environmental dredging and what do we not know. And that is in the context of published literature and guidance such as design guidance that both project planners and contractors who implement those projects have access to. One of the things we quickly realized is that we kind of needed to step back and start almost from scratch in terms of if we're thinking about trying to find a common basis for stakeholders, regulatory community, planners, contractors, kind of to use the same terminology, kind of have that same foundation in understanding of debris. A good place to start was a definition. So we proposed a definition in the WEDA paper. This one is very detailed, and I'll just present here the streamlined version, which is debris is non-sediment materials within the sediment matrix sufficiently large and strong to impact the efficiency or effectiveness of dredging, sediment management, or disposal operations. Next slide, please. Well, regarding environmental dredging, this schematic from 2008, which really at that time identified the key phenomena that are occurring during dredging that can contribute to both short-term and long-term environmental risk. Short-term risk, thinking in terms of the water quality during the dredging process and the outcome of dredging and whether the outcome is achieving the remedial action objectives and whether the process can be managed in such a way that the effects of dredging are mitigated. So this schematic is intended to kind of represent that in a cartoon form. So the dredge bucket in this case is interacting with the sediment surface. That creates disturbances of the sediment. Oftentimes that sediment is resuspended and moves with currents. When that sediment is resuspended, it can interact with the water column and potentially release dissolved contaminants of concern to the water column. Then that disturbed sediment can eventually, and it can be a period of time, can resettle down to the sediment bed as residuals. And those residuals, it's important to point out, can be entirely different in their properties compared to the intact sediment, meaning it can be less dense, it can almost behave as a liquid, and therefore it's difficult to redredge, and it may move to other areas, potentially away from the dredging operation altogether. And that ultimately combines and contributes to the environmental risk, the other R. But we don't see debris in this depiction, and we wanted to examine that more closely. Next slide, please. So within the paper, we proposed a definition, as we saw. We tried to develop some planning tools to help with understanding debris, whether it's thinking about the feasibility study stage of a project where you're weighing one alternative versus another, or the actual design of the project. We described some of the considerations that debris will have on the 4 R's for dredging that we just covered. Talked about debris impacts and some of the characteristics of debris that are important to try to better understand to plan the project. We also provided, and in part from the input from contractors, a range of construction operations that can be employed for debris for both mechanical and hydraulic operations. Next slide, please. So we're not the first to think about debris. Debris is covered in the literature and in guidance that is out there. It's just covered at a high level. That guidance does acknowledge the fact that debris is an important factor for both the environmental considerations for a project as well as the operational factors. This specific guidance documents recognizes that debris can provide increased resuspension, generation of residuals, and affect the production of the dredging operation. Next slide. But that particular guidance does not go into additional detail. Sorry, next slide. So here is that same schematic, but with some large debris added to help us think about what some of the during dredging implications may be, both environmentally and operationally. So when the bucket is encountering the sediment bed, if there are large debris in particular at the surface or embedded within the zone of influence of the bucket, that can actually impact the ability of the bucket to penetrate the sediment, which would require additional attempts to get the sediment, which is ultimately being targeted for removal, that is around and below the debris. And then as that bucket tries to dislodge and remove the sediment, it will pick up debris along the way. In doing so, that debris can contribute to the creation of voids, for example, that residuals can find their way within. It will obviously create additional disturbances of the sediment that contributes to the resuspension process, et cetera. And then as the debris is being lifted through the water column, sediment that's adhered to the debris itself in some cases, and then if the bucket is ajar and held open by a large piece of debris, then you can have losses entirely through the water column. That's something we need to think about. Next slide, please. And this just is a quick illustration of an interesting fact that our ability to deal with debris and more complicated, larger and heavier debris involves tools, as you look kind of left to right, that are more robust. But what you'll notice is they also are not fully enclosing the sediment that is being removed or the debris. And that's necessary. Those techniques are necessary to get the large debris out. But on the left-hand side, you kind of see an environmental bucket, which is specifically designed for precision dredging. That those buckets can remove thin layers of sediment. They do that in a way that provides a level cut. The bucket fully encloses. Those buckets are typically lighter weight, and they're not really designed to remove debris unless it's nicely contained within the bucket. In the middle photo, in the background, you see a conventional clamshell bucket attached to a crane. Those are heavier. That has a better capability to remove debris, but the top of that bucket or any bucket like it is open to the water column. So that could be, the disturbances could be taking place there. And then on the far right is a grapple that's needed for the most complicated debris, and that really has no ability to contain the sediment. Next slide, please. And then we think also in terms of hydraulic dredging operations, which has some of the similar considerations for, again, both environmental and operational impacts. In this case, though, the hydraulic dredge which is essentially like a vacuum below water. There is typically a cutter that's dislodging sediment. In proximity to the cutter, below the ladder is an intake to the pump and the pipeline. That intake is a very finite size, could be 8 inches or slightly larger. And so there's only a certain amount of debris that could get through that. And in fact, contractors may intentionally try to limit the debris that gets entrained in that process because of the downstream processing that needs to take place. This type of operation, the dredge move side to side, so you can see that may kind of skip over, jump over debris, provide some additional disturbances. And similarly, as with a bucket, these dredges need to come out of the water. So when you have to lift these up for maintenance or dislodging debris, then that will also release sediment to the water column. Next slide, please. And this is just a table that is in the paper, but it summarizes some of the factors that we just went through. And in the table, we just tried to identify some of the more key considerations from those 4 R's that would be in play during those operations. Next slide, please. We also wanted to think about categorizing our understanding or the degree of uncertainty that we have for a given site in regards to debris. Unexpected debris versus expected debris. Unexpected debris would be something you think about for buried debris in the sediment subsurface within the volume of the sediment that has to be removed. There are limited techniques available to us to really truly understand what buried debris looks like for a site. But our goal is generally to get as much of that unexpected debris into the expected debris category. That can start with review of the operations for the site history. Even at the feasibility study level, a lot of effort can be put into trying to ascertain what the debris picture might look like for the site. And that can lend itself to improved planning for investigations, some of the investigations that we'll go through in subsequent slides here. We further divided expected debris into these other definitions, and that's really just showing an increasing understanding of debris. If you anticipate the debris more based on site history and anecdotal information, if you start to understand the location of that debris, we call that identified debris. And then finally, you reach a point where you have characterized the debris, and that's kind of the best position that you can be in from the project planning phase moving into the construction phase. Next slide, please. So the key parameters that we're looking for in a feasibility study or design is these items. We want to understand the types of debris present. If it's wood, metal, concrete, those each have different considerations and implications. The size of that debris, smaller debris that can be easily contained within an environmental bucket or pass through the intake of a hydraulic dredge may or may not be even important in a sense. I mean, it's always important, but larger debris that may drive additional operations, may drive additional handling steps, may require specific disposal considerations or special disposal considerations, as well as other factors like the distribution of debris. Is it localized within an area of the site that was active for an aspect of its history, or is it completely distributed throughout the sediment? And ultimately, can we reach a point where we can quantify that debris? And then, as we previously covered, the environmental factors are also key. Next slide, please. Oh, and I'm sorry, I wanted to point out that photo. I don't know if you can go back one, Amy. Sorry. That photo at right is from one of our projects. We were able to identify these cars, I'll show on an upcoming slide, using multi-beam bathymetry. And as a result of being able to identify those debris items, we were able to, in the design, plan for a separate removal operation with this grapple. And you can see we also were able to plan environmental protection measures. There's a turbidity barrier in the left corner there. But that came about because our investigations were able to identify these features. Next slide, please. So if we think about drilling down even further to trying to characterize debris, in the left-hand column or column there, we identified some parameters that we felt were important for that. Unit weight, total weight, the embeddedness of debris, whether it's at the surface or, for example, maybe it's a log that's fully embedded through the entire thickness of removal. So if you have, there are aspects of these characteristics that can drive problems ultimately. So we wanted to think about that and put a relative ranking. So on the embeddedness example, you would expect, for instance, that a log that's embedded fully through the thickness of removal will create additional resuspension and residuals above and beyond what you would expect for the sediment itself, and so on and so forth in the table. Next slide, please. And then this is another tool that we developed for the paper. Obviously, you can't see any of this, and that's okay. What we did here, just to introduce this, is we thought about every piece of debris we could possibly think of, and we tried to place some context to that. So we, with a bullet that you can see, we just did a yes/no on whether or not that particular debris might be important in terms of either those debris characteristics that we just covered that can drive problems. But we also thought about it in terms of the entirety of the operations process, from dredging, dredge material management, so the transport and handling of the sediment and debris as a combined volume, and then ultimately the disposal. So again, this is just intended to be a planning tool, and we included that in the paper. Next slide, please. So just conceptually, one would expect that as our understanding of debris improves and we get to the point where we are able to characterize the debris and get at least some indication of what these parameters that are factors that can drive problems are, if we can some way that allows us to think about the project risks, plan the appropriate requirements, and include that in the design specifications for both environmental protections and some of the operational considerations. Next slide, please. And then conceptually, one would think that, and all this is really meant to portray, is that, again, as we increase our understanding of the debris, it can affect the outcome for project costs. So if we go into a site that we do not have a lot of knowledge of debris, or the unexpected debris is just significant and there's no way that we can truly characterize that, one would expect that during the construction phase, when the contractor is out there and encountering this difficult unexpected debris, costs would be on a pretty steep trajectory for each of the debris items that are encountered, and that's in the red arrow. But if there is some upfront investment to do investigation activities, then you may find yourself on a flatter trajectory where the cost per item is less because you're able to account for that, and the contractor is able to also account for that in how they're executing the project. Next slide, please. So this is an example from that previous slide. We saw the car. On the right-hand side is the data that ultimately led to the conclusion that those cars were there. In this case, it was as simple as multi-beam bathymetry, which is a data type that is very common for dredging projects that occurs very early in the project phase. So maybe the thought here might be is if the conditions are right and you have the ability to choose between a single beam or a multi-beam type hydrographic survey, a multi-beam that provides a higher resolution outcome could provide benefits like this, where you're able to actually see the debris at the surface. The multi-beam bathymetry has been an effective tool for us, as well as some of the others listed here. This is not a comprehensive list of investigation technologies. This side scan sonar, and then if you need to get a closer view of the debris, there are technologies like remote operated vehicle, and even diving, which is fairly rare but can be employed. There are also other technologies like magnetometer and sub-bottom profiling that can be used. But in terms of trying to understand debris, those are difficult techniques to get good conclusions about the debris and the quantity of debris, given their limitations. The timing is important, and we would recommend trying to get as much information as early in the project as possible. That can contribute to providing more realistic alternatives and feasibility studies on both, what the operations would really need to be to manage the debris, and therefore the cost of the project in the feasibility stage is more representative, maybe helps decide the better alternative. And then that also, if debris is found to be an important factor for the site, then the design phase, construction phase, those are both opportunities to expand the investigation to better understand the debris itself. Next slide, please. This is an example of a side scan sonar mosaic from a project that we had in a lake setting. It's about between 150 and 200 acre mosaic. And it's kind of tough to see some of the features, but as you start to drill down into this and zoom in, unfortunately, you start to see artifacts. Those vertical lines are actually just the limits of the survey transect. But then the resolution is so high that you can zoom in and see. In this case, we were looking for wood debris, and we were able to see clusters of debris that helped us. You can kind of see in the surface texture that helped us understand this particular site better. Next slide, please. And this is a remote operated vehicle example. In this case, we were wanting to get a better look at the debris that we expected in front of a wharf structure. And this was in a fairly low visibility situation with the water, and yet the ROV, you can still pick up these large riprap sized stones on the sediment bed. We need to get to the sediment below that to remove it. And so, that might lend itself to questioning, well, whether an environmental bucket could even remove that. So maybe we need to bring a conventional bucket to the site to remove that material. Next slide, please. And this is an example, again, from the kind of the acoustic sonar perspective. This is high resolution sonar, which is very similar to multi-beam survey turned to its side to look at waterfront structures. So in the examples here, you can see intake structures, and you can see, a small pier, and that may help us zoom in to think about some of the debris that may be in and around those features. Next slide, please. So with everything, there is an investment. For the most part, when the debris quantity is significant, or there is going to be complex debris, large debris that may require special operations and handling, it's very likely going to be justified to do the investment to conduct investigations early in the project. But this is obviously a cost analysis that needs to be done. There is an investment needed. If the debris situation at a site is not anticipated to be problematic, then that may influence the amount of investment that really needs to be made for effective planning. Next slide. So as we think about the many questions there are to answer in a feasibility study or design, I listed some of those here. These are questions that not only the project planners are thinking about, but the contractors are thinking about these same questions when they're preparing their bid. And that bid typically needs to be prepared in a very short time frame. What tools and techniques are going to be required to remove the sediment? What special requirements for maintaining water quality, or other, employing the appropriate environmental protections to protect water quality and to manage the short-term risks from environmental dredging. To get additional insight, as I said, we had a debris questionnaire we sent to contractors. This next slide, we appreciated the feedback very much. It really helped us out. The next slide is just a quick high-level summary of some of the feedback that we did receive. And I'll not go through all of this, but kind of focusing more on the right-hand side, I thought was interesting because all the contractors said the same thing in terms of really more guidance is needed out there on debris. And it's not just to get the contractor enough information to properly plan the project. And so that we're all kind of speaking the same language, and we have a mutual understanding, again, whether it's environmental agencies, natural resource agency, stakeholders, planners, or contractor on how to refer to this debris, how to effectively plan so that the contractor can be fairly compensated for that debris, and have enough information that the contractor can plan important aspects, like, for example, if the landfill will have special requirements for either accepting the debris based on its size, based on its composition, or some of the other factors that we discussed earlier. So I think at this point, we turn it over to Matthew Bowman for his part.
Thanks, Jamie. I'm Matthew Bowman. I'm EA's Chief of Construction Management, and I'm going to take the time that we have left to talk about debris and its impact and management during remediation. I'd like to start again by thanking the contractors that shared their knowledge and experience with us about debris management. It really helped the development of this paper and the slides. And, in particular, J.F. Brennan, Sevenson Environmental, Envirocon, and White Lake Dock and Dredge were all very helpful. So, as Jamie alluded to earlier in the presentation, debris has a lot of impacts, and construction is no exception. The construction sequencing obviously could be changed in terms of having a pre-dredge debris removal event. It could also impact the kind of dredging you do, whether you do hydraulic or mechanical dredging. We'll talk a little bit about that further in the presentation. It may require special equipment or special attachments, such as skeleton buckets or grapples, to address the debris at your site. Certainly, there is a production rate impact on sites with high hits for debris materials. And it can cause increased downtime and equipment maintenance, particularly for hydraulic dredging, which its nemesis typically is steel cable and wire that sometimes we find in industrial waterways. Impacts to marine construction, like the structure in the picture shown here. This is a combination wall, but other marine construction features that appear on these projects are cofferdams, steel sheet pile structures, as well as bulkhead construction, and subsurface obstructions can really have a significant impact on the ability to construct those features. Debris segregation and processing, I'll talk a little more about that later in the presentation. Certainly that effort can be fairly modest when dealing with debris, or it can be very significant depending on its characteristics and disposal needs. Disposal quantities, how you characterize the material, and even the options of how you can deal with the debris depends a lot on the character of the debris and the sediment that you're working in. It can also interfere with the post-dredge decision for making framework, making it more difficult to sample, as well as create cap integrity issues with embedded debris that may come up through and impinge on the continuity of a sediment cap. And then finally, kind of the understatement of the year, debris can affect your project cost. It can affect your schedule, and it can create contracting challenges. And, in a worst case scenario, something we saw a couple of years back, literally a contractor had to demobilize from the site, and debris had to be rethought on the project so that the contractor could successfully execute the work. Next slide, please. So, contractors have a lot of different approaches that they can use to address debris issues, and it really differs in some ways based on the kind of dredging that they're doing, mechanical versus hydraulic. Mechanical has the advantage that has a little greater capability of actually working in and around debris. And, depending on the buckets that they use, whether that's a clamshell or an environmental bucket, they do have the capability of removing some debris as a part of the dredging matrix, and even using that same bucket to pick specific objects out so that they can be managed. That's not to say there still isn't sometimes a pre-removal event that occurs for surface and embedded debris. And they also sometimes switch to specialized attachments, as I mentioned before, like grapples and rakes and even a skeleton bucket to try to go after cobbled material. Hydraulic dredging, while obviously an excellent approach for many projects, has some challenges in particular with debris. And if that material can't go through the intake of the hydraulic feature, and that's often governed by the size and positioning of the Gatlin plate on the intake, it really just pushes debris around, or the debris becomes simply problematic for the equipment itself, like I mentioned with cables and wires. Debris handling, segregation, and processing, these are all things that contractors typically are used to working around, and we'll talk a little more about these later. As I said, this can be a fairly minor impact or event for the project. In other cases, it can be fairly involved and manpower intensive. And then debris contingency planning, which is something that probably should be on most dredging projects, is thinking through the historical uses of your site, the knowledge that you have about debris that's currently present on the site, and then trying to project potential impacts that you may have on your project in the subsurface so that you're prepared to deal with them when they occur. Next slide. So on the topic of pre-dredge debris removal considerations, I just have a little bit of information here about the basis for that decision and, some of the planning considerations that you would want to make if you're going to pursue that type of operation. As I mentioned already, hydraulic versus mechanical dredging approach. Hydraulic it needs a pre-dredge debris removal event more commonly than mechanical due to mechanical's innate capability of sometimes dealing with smaller or small medium sized debris. Accessibility, the quantity, the distribution, the size of the debris will really dictate the type of equipment that will be used for this kind of activity. And using the terminology from the presentation already, identified and characterized debris, those are the ones that we've located and we understand what they are really the only types of debris that can be efficiently mined using this particular approach. Oversized debris, like the cool picture that Jamie showed of the car getting picked out of the Lower Rouge River, those are perfect targets for this type of operation because none of the standard dredging equipment will be capable of dealing with those, and certainly they're large enough obstructions that would make dredging around them very difficult. The next two are related. You need to understand your ability to control resuspension of sediments that occur when these objects are removed, and what kind of regulatory and permitting constraints you have or you need to consider in terms of protecting water quality. And then finally, cost efficiency. Are there enough objects? Are they enough of a constraint on the project that an advanced removal of these objects are cost effective? So the removal planning, you consider resuspension controls. How are you going to control the 4Rs when you remove these objects to the degree you need to? It's mostly a regulatory and permitting question, but you need to be prepared to meet those standards. What kind of equipments and attachments are you going to use? And on top of that, have you considered the draft that you have? Because many times these objects are targeted before dredging occurs. So the draft is typically the shallowest at any point in the project at the beginning when these objects are sometimes removed, as well as your reach. In these industrial waterways and urban waterways, a lot of the debris tends to accumulate right at the edges near existing structures and shorelines. And so some thought needs to be given. Is it appropriate to cut or shear these objects instead of tugging on embedded debris that has accumulated at these locations where they could compromise shoreline stability? And then finally, some thought should be given to whether separate or overlapping windows with dredging occur. Some of these projects have a number of debris removal events that occur throughout the project, and based on your understanding of the debris and its distribution will drive that, as well as your general size and geography of your work area. Next slide, please. So, some of the 4R considerations here, when you pull these objects out of the water, obviously there is going to be resuspension of sediments. There could be sheening or releases of NAPL that occur from embedded objects, as well as the process itself of picking these items, transporting them, processing these debris materials will generate water too that will have to be managed and potentially treated and disposed of. Turbidity barriers and sorbent booms are pretty common tools that are used to protect water quality in the areas of where debris removal is occurring. In some cases, some projects have more robust features like cofferdams combination walls, steel sheet pile walls, that are employed as containment barriers for the project that certainly should be factored in to the timing of when debris removal occurs. Moon pools, just another configuration of turbidity barriers that could be used on a project. And water generated in the scows or for temporary storage on deck barges often needs to be contained. The question obviously is a regulatory one and a permitting one, but simply blocking the scuppers on the barge and then, managing and controlling that water inside the barge periodically may be necessary. And while the water quantity generated from debris processing and debris management can be pretty small, or it can be very significant in like a debris washing event, for example, water treatment needs to be considered as appropriate. And then finally, another potential best practice that could be used are air curtains, which are basically bubbles that are brought up near vessel entrances or exits that again help control resuspended solids from leaving the work area. Next slide, please. So debris risk management. I think Jamie said it very well. This data that we want to gather on debris, obviously, whenever it's practical and whenever it's cost effective, really getting that data early on is really important to the project because it will create a more informed design and a better prepared contractor to tackle the debris challenges of your site. One of the common themes that came out of the contractors that we interviewed almost universally is this idea of risk sharing. In a lot of cases, these projects, debris management tends to be a lump sum item and basically a contractor risk that they are required to manage based on assignment in the contract. And that can be pretty challenging to estimate and pretty challenging to prepare for. And, when I was hearing this from the contractors, I was thinking back to the Construction Management Association of America's risk principles, which really, when I went back and looked at them, they really apply to this situation. And I'm not going to read those to you down at the bottom of the slide, but I think they are applicable. And I think that it does suggest that this is a risk that probably should be shared. And perhaps contingency line items in a bid, maybe unit costs for managing debris, or even on one site, we had a time and materials price for the equipment standby, so that it's prepared to deal with debris as it's found, and then a unit cost when it's actually operating. Clear direction and contract and technical specifications, really, really important. And it's important that debris is defined in those documents. It's important that proper direction is given on how debris is to be managed and disposed of. And then finally, some real information about risk assignment as to who is responsible in the contract documents for each step of the debris operation. And then finally, contingency planning. I mentioned contingency plans already. If you have a risk register for your project, even if you have a site that doesn't have a lot of debris, I think it would be an excellent thing to include on your risk register and plans for mitigation for debris. Because in many cases, it's not entirely impossible that you could be surprised by what you find in the subsurface of your site. Next slide, please. So briefly, I'm going to touch on debris processing and segregation. Really, these operations tend to be driven by your disposal requirements for your contaminated sediments and for the debris itself. And the most important elements typically are the size, the geotechnical properties, and the chemical constituents of concern associated with your debris. We had a project in which the incinerator had a limitation as to the kind of debris that they could take, as well as the size of the opening. And so we actually had to have a debris washing and manual segregation process for debris. And that picture in the the lower corner of the slide shows the washed debris after we were done. Just because that's basically for us to be able to deal with this very contaminated sediments, we needed a way to get the debris out of there and take as little of the sediment with it as possible. There is some practicality that needs to be considered with recycling. I know that, people suggest maybe that's an option from time to time, and I'm sure people have used it on their projects, but you need to weigh that against the challenge and time and effort that it takes to get your constituents of concern off that material safely so that it can practically be recycled. And then on some occasions, there are cultural and historical resources that have to be considered. I'm aware of a couple of projects that actually, sunken vessels were cultural and historical items that needed to be investigated and managed separately as a debris consideration. So some methods, point of dredging separation, it can be as simple as a grapple going down and grabbing a log and putting it off to the side in a barge. Or it can be more sophisticated and innovative depending on the type of debris you have. As like the picture here with Sevenson, they actually designed a special attachment on the end of an excavator so that they could separate sediments from cobbles. They had a lot of cobbles on a particular project, and they used this tool to be able to separate those. Barge segregation of large debris, that's pretty common. Put the big debris off to the side in the barge. Obviously manage any water that comes off of those. Mechanical screening, a little less common, but still done, with like a static grizzly bar screen, or something more sophisticated and less common, like a mechanical screen, like a trommel screen, that's designed to do a really good job of removing debris from the sediments. Hydraulic separation has been done on some projects using tools like centrifuges. And the interesting aspect of this is sometimes the contamination is really focused on the smaller particles. And by removing the cobbles and the gravel and the stone through hydraulic separation techniques, you may have a material that could be beneficially reused at the site and reduce your disposal costs. Debris washing and manual segregation, something I mentioned already, that picture in the lower corner. Some landfills require debris sizing. For geotechnical reasons, good reasons, they don't want full tires as they create void spaces. And sometimes it's as simple as just simply cutting a tree in half or a log in half so that it can fit neatly in the back of a truck on the way to disposal. And then there's always special cases that need to be looked at on a case-by-case basis of things like automobiles, appliances, and other odd things that are found in the river. Next slide, please. So just, these options aren't too much different than what you'd find with the contaminated sediments. The first two, the primary consideration, are mostly geotechnical. Are you doing a good job, with this material avoiding voids and avoiding differential settlement in these structures? And so those are the common considerations that drive being able to put debris in those locations. Metal recycling, we touched on that. Certainly a possibility. I haven't seen a lot of that in my experience, but I'm sure it's been done. And, beneficial reuse. Certainly a green thing to do when it's possible and when it can be done safely. Next slide, please. So the team just wanted to wrap up with some quick closing thoughts. Debris, these first two are kind of connected. Debris really requires some early attention in the project, particularly in the investigation, as well as the remedy and the construction phases. I think you'll get a better remedy design. I think you'll get better construction planning and construction execution the more you know about the debris at your site. Buried debris investigation, it's an opportunity for innovation in our industry. Finding subsurface targets that are non-metallic is very difficult. And, hopefully new technologies come online to help us look deeper into the sediments and understand the things that are waiting for us once dredging begins. Collecting site-specific data for the 4Rs for debris. There isn't a lot of literature material on that about site-specific data, and it would be something that would be great if there would be more of that could help regulators, help owners, help engineers understand better what are the 4R impacts when we remove debris. And finally, I would encourage everyone to consider, more risk sharing when it comes with the management of debris. I think there are benefits for all parties, and I think it will ultimately, in the end, reduce cost and better manage risk. So I'm going to turn things back over to Amy Lambert, who is going to have some follow-up information and some housekeeping items.
I don't see any questions yet, so I'll prompt you both with one while we're waiting. What has been the most significant dredging debris challenge that either of you have encountered to date?
Do you want to start, Matt?
I can, yeah. Probably would be one at a site in New Jersey where an enormous pocket of debris was located well below the subsurface along an existing bulkhead structure. And those particular sediments were located in a hazardous disposal classification and required substantial planning and kind of rework of our debris processing approaches to make sure that we manage those materials correctly. So it was a big surprise to us, and we knew that there were going to be some hits, but I don't think we managed imagine quite the amount that we found at that site.
And I would say for that one, actually a project that some of the photos from this presentation were from, including that big car. So, there are instances like that particular project where we really think we have a good handle on what's out there from all the work leading up to design and throughout the design, and have not only thought about the types of debris and their characteristics and their quantities, but have in our thought provided a means to compensate the contractor fairly and share risk, as Matt was mentioning. But even in those instances, in this particular project, there was more debris on the unexpected category than everyone anticipated, and it really added to the complexities of that project.
Thanks, Jamie. So we do have a question in the chat. As a chemical testing laboratory, would debris also require characterization? And how can these items be readily characterized?
That's a great question. I think about that more in terms of when you're planning the ultimate disposal for the debris. Are the constituents of concern in the sediment really significant enough that you're really driving some of the choices that need to be made for the debris itself? In that case, I think of things of trying to do your best to ultimately remove sediment from the debris. So I know that in the past, there have been activities such as taking wipe samples for debris. I think generally speaking in our projects, we try to reach a point where we have a good understanding of what needs to happen to the debris for its potential disposal options. And if the debris is small enough, I think it can be characterized, but again, I think it would be really more geared toward the sediment, which is ultimately the target for remediation. Matt, any thoughts on that?
No, I think you tackled it. I think it's a complex regulatory issue to make sure that you address these materials appropriately because, these are the circumstances in which maybe debris processing needs to occur to really do a good job of separating the debris from the contaminated sediments if they can't go to the same place.
Excellent. Well, I think that's the only question we've received today, or as of now. So we are coming to the top of the hour. I'd like to thank everybody for joining us. Matt and Jamie's contact information is on the screen. If you have further questions, feel free to reach out to them. And again, watch for the email from EA Communications with follow-up from this session. Thank you so much for joining us.